In this video, I would like to discuss the 6 basic logic gates that you'll encounter in digital electronics. So I'm going to go through these one by one and tell you what the name is, show you what's called the truth table, the Boolean expression, and the logic gate symbol. So let's start with the easiest and the most basic gate, which is called a NOT gate. And sometimes you may hear of this referred to as an inverter. And that's exactly what it does. So the NOT gate, the truth table for that, I've got the input here on the left column, the output on the right column. And you can see that when the input is a 0, the output is a 1. When the input is a 1, the output is a 0. And these are the logic levels. And some different terms you might encounter for logic levels. In this video, I will stick to using 0 and 1, logic 0, logic 1. Also, you might see off or on, false or true, low or high. And these logic levels actually correspond to voltages, which I'm not going to get into in this video, but what levels of voltage correspond to a logic 0 or logic 1. For this specific video, I'd like to just stick with logic levels, but these are some of the other terms that you may see. So this is the NOT gate. So the input is a 0, the output's a 1, the input's a 1, the output's a 0. We can also write what we call a Boolean expression. A Boolean expression, and this is the expression. The output is going to be on the left side and the input or inputs will be on the right side. So here we say that Z equals not A. So when you see a bar over a logic signal, that means that it's inverted. Okay, and then the symbol, the logic gate symbol, is this triangle with a bubble on the end. Okay, so the input A comes in. So if the input A is a logic level of a 0, the output of the gate for Z will produce a logic level of a 1. If the input is a logic level 1, the output will be a logic level 0. Okay? And so the way you state that in I guess algebraic terms is Z equals A with a bar over it. One other less common way you could see is something like this, an exclamation point in front of the A, and quite possibly you might see a tilde in front of the A, but by far the most common is going to be the bar over the variable to denote its inverse, its logic inverse. So that's how the NOT logic gate works. All it does, it takes its one input and it inverts the logic level of that signal to the other state. So a logic 0 will produce a logic 1 after it passes through the gate. A logic 1 will produce a logic 0 after it passes through the gate. So that's all there is for the NOT gate. Just a simple inverter. So let's move on to the AND gate. The AND gate can have multiple inputs, but for this video we'll just stick with 2 input gates. And what an AND gate does is it takes its inputs, and in order for the output of the gate to be a logic 1, all the inputs have to be logic 1. So if this were if this AND gate had 4 inputs, then all 4 inputs would have to be 1 to produce a logic 1 on the output. So here you can see that if 0 gets ANDed with 0. If a logic 0 gets ANDed with a logic 0, it produces a logic 0. If a logic 0 gets ANDed with a logic 1, it produces a logic 0. If a logic 1 is ANDed with a logic 0, it produces a logic 0. And only in the case where a logic 1 gets ANDed with a logic 1 does it produce a logic 1. And again, if this had been, say, a 3-input gate, then the only time the output would be high or a logic 1 would be when all the inputs were a logic 1. And the way we express that as a Boolean expression is we just write z equals a, b, just right beside one another. Sometimes you may see like a dot in between the a and b to denote and, but if you just write them right next to one another, that also implies the and function. So either a dot, or if you just write the terms that you're anding together, right next to one another with no symbols in between. Okay, so that is the and function. So the thing to remember about the and function is that all inputs have to be logic 1 to produce a logic 1. Now moving on to the or function, the or function only requires that one of the inputs be a logic 1 to produce a logic 1. So for the or function, 0 or 0 is going to produce a logic 0. 0 or 1 will produce a logic 1. 1 or 0 will produce a logic 1. 1 or 1 will produce a logic 1. So again, if this were a 3-input OR gate, then it would always produce a 1 on the output except for the first row where all the inputs are 0. So when all the inputs are 0, it's going to produce a 0 on the output. Otherwise, it's going to produce a 1 because you would have at least one of the inputs being a logic 1. Okay, so that's the OR function. Now the NAND is a combination of the and the not. So you can see on the gate here, the gate looks like an AND gate. Looks like an AND gate, but it's got the bubble from the not gate. It doesn't have the, we don't draw it with the triangle with the bubble. We just put a bubble. On the output of the AND gate. So this is essentially saying that we're doing an AND function and then we're going to invert the output. Okay? So this truth table will be, the output will be 1, 1, 1, 0, which is the inverse of the AND, which is 0, 0, 0, 1. So you do the AND function, you get your output of your AND function is 0, 0, 0, 1, but then you invert that, excuse me, because of the bubble on the output. So that will give you 1, 1, 1, 0. And again, just like for the not, remember on the not, we put a bar over the A, showing that we're inverting it. For the NAND, we put a bar over the AB term. Okay. Now it's very important that the bar be placed over the entire AB term, not putting a bar over the A and then a bar over the B. So the bar needs to be over the complete A ANDed with B term. So this is what the NAND gate logic symbol looks like. And as you can probably guess, for the NOR, it's the same as the OR with an inverter. So we've got the OR gate with a bubble on the output. And so if we look at the NOR gate truth table, 0 ORed with 0 would be a 0. but then I invert that to a 1. And then all the other rows, I have at least 1, 1 in the inputs. So the OR output would be a 1, and then I would invert it to a 0. Okay. And again, here we put the bar over the entire A plus B term. Just like for the OR, we had just A plus B. The OR is Z equals A plus B. The NOR, Z equals A plus B with the bar. Now, the last one we'll look at is the exclusive OR, which is XOR, and you may hear the term inclusive OR, which really is just the basic OR gate. We don't usually say inclusive OR, we'll just say OR gate for short, but the exclusive OR, we have to differentiate that. Okay, so the XOR gate looks like this. So we have we put a circle around the plus sign to indicate exclusive OR rather than inclusive OR, which would just be the plus sign. Okay. And then on the OR gate, we just put a little tail or fin on the back side of the OR gate to denote that it's an exclusive OR. Now, the only difference between this and the inclusive OR is this final row. So if you remember, for the OR gate, a 0 or a 0 gives you a 0. And here, 0 or 1 is a 1 or a 0 is a 1. Here we have two 1s, which would be equal to 1. It would produce a 1 for an OR gate, but for an exclusive OR gate, it produces a 0. So this is the only row in these two input tables that's affected, that's actually different from the OR gate. And it's one way you can look at it as well. This is really comparing these two values. So if the two inputs are the same, so let's say both inputs are 0, then it's going to produce a 0. If both inputs are 1, it's going to produce a 0. It's only when both inputs are at the opposite logic levels that it will produce a logic 1 on the output. So it's essentially comparing the two logic values. So that is a summary of how these 6 basic logic gates work. And of course, these are just the individual gates. These will be connected up together to produce useful combinational logic circuits. But you need to understand the fundamentals of how the individual logic gates themselves behave before moving on to combinational circuits where we can connect these together to be able to perform some functionality. So that will do it for this video, and I hope that this has been useful, and that's all.